All right, welcome everyone. Thank you for joining me this morning for how intelligent query processing improves T-SQL performance. Super excited to be here. This is my first virtual SQL Saturday, although I've been doing SQL Saturdays for many, many years. If you're not familiar with me, here's some bio information about myself. I work for a company called SentryOne, one of the sponsors of this event. And for what it's worth, I am going to be hosting office hours immediately starting after this presentation concludes, and then later on this morning at 11:30, I'm actually going to be giving a more kind of semi-formal presentation called Going Beyond Monitoring with SentryOne. But in either case, that's enough of the SentryOne stuff. What you're really here for is to learn about intelligent query processing. But before I dive in, please do make note of my contact information, my Twitter handle and my email address. I love to help people out. I love to, talk to folks and engage with the community. This community has given me so much over the years, so I encourage you to reach out. If you have questions, if you want to, chat, do some follow-up chatter or whatever the case may be, I'd love to talk to you. All right, so enough of that. Let us continue. So, have you ever asked yourself these questions about your T-SQL code base? For example, you've inherited some stuff, or you just joined a brand new company, and you're looking around at the T-SQL code that you're dealing with, or it's that one application that was built 10 years ago that's still in production and still a key core application that's very fragile, and there's not much you can necessarily do with it. You can kind of take some steps to inherit it, but there's certain issues with it, and performance is real. Correcting performance is really a struggle, and maybe a lot of that T-SQL code base is stuff that it would be a major endeavor to rewrite it and whatnot, right? We all have different applications of that nature. Now, wouldn't it be nice if we had that easy button that we could just simply press to magically fix performance? Of course, we really don't have that, or do we? So Microsoft is making some really interesting changes in various versions of SQL Server, particularly in SQL Server 2019. But there's a little bit of history with even more recent prior versions of SQL Server before 2019. So let me go through a brief history of more recent changes and improvements that Microsoft has been making over the years to query processing. In SQL Server 2014, Microsoft introduced something called the new cardinality estimator. The cardinality estimator's job is all about making estimates and figuring out how much information is inside one of your tables. I love analogies, so let's pretend you have to go out to, or you have a box in front of you and you have to pick it up. Do you have any idea what's inside of it? You think it's going to be full of books, which are very, very heavy. So you think it's going to be a very heavy box. And then when you actually lift it up, you'll figure out whether it's really that heavy or not. But it's the art of making that estimation of how heavy do you think this box is going to be. That's the job of the cardinality estimator. And as such, when it comes to coming up with your execution plans, SQL Server makes various decisions, the Query Optimizer does, as far as, based upon estimates and statistics of how much data is inside each of these different tables, which will impact the decisions that it makes on how to access that information. So in either case, in 2014, they came up with a brand new cardinality estimator to help make improvements. And then in 2016, amongst the various improvements, the one that I particularly want to focus on as far as query processing is concerned is the query store. Now we can actually store history of executions and all sorts of other really powerful metadata. And by having that history information, the query processor is now able to take actions, or we were able to do things like plan forcing and other really cool new features. In 2017, Microsoft introduced something called adaptive query processing. Adaptive query processing had a number of different sub-features underneath it, but one of the things that bummed me out about adaptive query processing was that it was, for all intents and purposes, really only available to column store constructs. And frankly, not a lot of people have adopted column store. You really should. You should really look into it because it's really, really matured over recent years. But there's still a lot of people that are behind. Or again, if you have that old legacy application, it definitely doesn't have column store. So you really couldn't benefit from adaptive query processing. But now, adaptive query processing has now become intelligent query processing, and it now allows us to essentially rewrite history. What do I mean? Well, let me walk you through a quick overview of what happens behind the scenes with the query processor when you submit a T-SQL query. that T-SQL query gets passed to the query optimizer, a whole bunch of magic happens behind the scenes, but what results from it is an execution plan. This is the game plan that SQL Server has decided to do to execute, that it'll pass along to the storage engine. So it's the execution plan that dictates that I'm going to do an index seek here or index scan here. I'm going to use a merge join. I'm going to do these types of physical operators. And unless you're cheating and using things like hints, you don't dictate that inside your T-SQL query. You just say, get me data from table A, join it to table B, so on and so forth. It's the decision of the query optimizer to say, I'm going to do an index seek against this table or an index scan against this table. The key detail to remember here, though, is that once the query optimizer comes up with an execution plan, it is set in stone, right? There's no way of going or changing it once you begin execution by the storage engine. But that's where things change now with the intelligent query processing. We can now start making changes to the execution plan in certain interesting ways during execution or at execution or post execution for subsequent executions. And that's one of the cool things that intelligent query processing now kind of brings into play. Okay, so for the purposes of our discussion today, what we're going to be focusing on are developer topics or things that are just focused really around T-SQL. So the first topic we're going to be talking about is something called table variable deferred compilation. The second topic we're going to talk about today is inlining of scalar user-defined functions. And then we're going to talk about batch mode for row store and some of the capabilities that come to us through batch mode for row store, which are adaptive joins and memory grant feedback. You'll notice that there's a little asterisk there. That's because adaptive joins and memory grant feedback were technically introduced in SQL Server 2017. However, they were only available for batch mode for column store. Remember my comment about column store earlier. So that's one reason why it's now even more available to us now, because now it's batch mode for row store has been implemented in 2019, and therefore, as a result, we now get the benefits of adaptive joins and memory grant feedback for row store when we are using batch mode. So in either case, this is our agenda for this particular presentation. Understand that this will move fairly fast. This is meant to be an overview, but all of my code and the slides are all available up on my GitHub. So just remember my Twitter alias, SQL Beck, or again, it'll be on the final slide as well. All right, so let's go. First, let's talk a little bit about table variable deferred compilation. So let's think about a little bit of history here. I've always hated table variables. Table variables, in my opinion, are absolutely evil. A variable in of itself, though, is just a construct that holds a single value, and its scope is just scoped to that particular batch or that little session or whatever. Whereas a table is persistent and it can hold a whole bunch of different values, both vertically and horizontally, right? Depending on how many columns you have and so on and so forth. So at some point in the past, I want to say it was like 2005, Microsoft had to kind of check off a box, if you will, and create something called a table variable. So it tried to give you the best of both worlds, something that you can just declare on the fly, but it gives you greater extensibility of the table by having columns and allowing you to store multiple values inside that table variable. And a lot of people thought this was really, really cool. There was a common myth that table variables were only persisted in memory, and a lot of people started using them. Unfortunately, table variables have a huge drawback, and that comes around with the query optimizer. Remember that I said a variable, a regular plain old variable, only stores one value inside of it. Well, unfortunately, when it comes to the query optimizer and estimates and trying to figure out how much data is inside of it, the query optimizer assumes that a table variable only has one value. They did make some changes in more recent versions prior to 2019 to try and improve that, but it's still a very, very poor estimate. So if you have 100,000 records or millions and millions of records inside that table variable, SQL Server still thinks there's only a small or one record inside of it, and will then therefore make some horrific performance decisions in the execution plan. So to that end, let's break down how this all works, and then I'll show you what has been done in SQL Server 2019 to improve all that. Okay, so for our demos, I use a database called the Auto Dealership Demo. It's also available up on my GitHub, and I just have to do some setup here. I'm just going to be disabling a few things here. Now, one of the cool things inside SQL Server nowadays is something called database scope configurations. This one allows you to turn on and off all of these really awesome different features. And you can do that for specific databases as well. So I'm going to turn this on over here, or run this code just to show you that deferred compilation table variable is currently set to its default value, which is to be turned on. Okay. So we're going to actually turn it off, so that way I can show you the behavior before SQL Server 2019, essentially, like pre things. So what I'm going to do is just a little bit of setup here. So because we're going to compare and contrast temporary tables and table variables as part of this example. So I'm just going to be creating two temporary tables, one called temp customer and another called temp sales history. Into temp customer, I'm only going to insert one record, and then into sales history, I'm going to insert 500,000 records. Okay. So this is just some setup code. And then I'm also going to create some clustered and non-clustered indexes on these guys, just to make sure that we have optimal execution plans here. Okay, so this is our baseline. So in this case, I'm just going to do a join between these two tables. Remember that sales history has a bunch of data inside of it, and customer only happens to have one inside of it. I'm going to turn on actual execution plan and execute this guy here. And then we're going to look at set statistics IO and set statistics time just to see the output. From a time perspective, this was this one down here, it was insanely fast, 26 milliseconds. And then from an IO perspective, not very much IO, 6 logical reads, 2 logical reads, as I would expect, because we're doing a clustered index scan against customer ID, but there's only one value inside it anyway. And we're doing a nested loop join. This is the key detail, and then we're doing an index seek against sales history here, because for one customer, we just want to get the sales history for that one customer here. The key takeaway, though, is that we're doing a nested loop join here. The idea of a nested loop join is that if it really excels when you have one data set on one side that has a very small amount of data, and then another data set that has a whole bunch of data. So in this case, customer only happens to have one, and then sales history has a bunch. Because what it'll do is that it'll look at customer, in this case, grab one customer value and then go seek inside sales history for everything that matches. But if there are multiple customers, I then go back to the customer table again and then go out to sales history. So it's an iterative almost kind of operation, or like a cyclical kind of operation. So you can see how repeated scanning through sales history could really add up if we had a lot of customers. But again, this really excels if we only have a very few customers, in this case only like one in this case. Okay, so now what I'm going to do is I'm going to set up a table variable. It'll be identical to the customer table, so that's my table variable here, and I'm going to insert in the same exact customer ID that happened to be in the temp customer table into that table variable, and then I'm going to run my joins again. First, I'm going to do a variation of the joins that it's a table variable to a temp table. Then I'm going to run the temp table against a temp table so that we can compare and contrast the two. And in this case, we have a nested loop join once again, and then another nested loop join for the temp table versus the table variable. But then, let's see, and then underneath the messages tab, table variable, 2 logical reads, 6 logical reads, no big deal, because again, it's a small amount of data. So that's kind of our baseline. This is the ideal situation when you just have that one value, right? However, what if you happen to have a whole bunch of values? So I'm going to reset temp customer here and toss in 500,000 records. And then we're going to rerun our comparison here. So I'm going to do the temp table and the table variable and populate them and do that compare and contrast. So now in this case, let me expand the result window. Notice that once again, for the table variable, we have a nested loop join here. And the devil's in the details. Our estimates are very, very low. However, our actuals are ridiculously high. This is not good times. So what we wound up doing is a whole heck of a lot of other extra work here. So, if I look at, the clustered index scan, we only executed one, but we pulled out, 500,000 rows here, even though we only estimated number of rows was 1 here. So this is not good times. So as a result, my index seek, even though, oh, it's an index seek, who cares about that? But we index seeked 500,000 times, so it was 500,000 index seek operations. And if you check out my I/O presentation about how to improving I/O for a T-SQL performance, you'll have a better understanding of why this is a horrific anti-pattern. But that's a whole separate topic in of itself. But let's look at it from an I/O perspective, just to see the proof in the pudding. From a table variable perspective, we did 1,000 logical reads against that first construct, but then against the temp table here, we did 1.5 million logical reads because we had to go after it 500,000 times, one per customer. As opposed to the temp table version, by the way, we got a different type of join, a hash match join. A hash match join excels when you have two large sets of data here. So that's actually a better decision based upon the estimates. And as a result, the I/O here was a heck of a lot better. 800 and 1,000 or so. So yeah, heck of a lot less I/O because we had a more ideal join. And then from an execution time perspective, 1,900 versus 1,300 milliseconds. And also notice the time on the CPU was a little bit less as well. So simple example of how table variables can really, really burn you. That's in the days of old. Now with deferred compilation, what SQL Server 2019 is going to do is defer the compilation, so therefore it's going to defer when it comes up with the execution plan and sniff the table variable at runtime to see how much data is inside of it. And this will hopefully help us out. So let me turn this back on. Now I'm going to rerun a comparison test. Okay, first looking at the execution plan. In this case, I got a different kind of join for my table variable example. I got a merge join instead of a nested loop join. That's better. Remember, I had already put on indexes onto these guys, and therefore a merge join actually really excels when you have two sets of data that are already pre-sorted. So this is actually pretty good. Let's actually look at the properties. Estimated number of rows, 500,000 from the table variable. This time again, SQL Server has now sniffed it. That's the benefit of this. So this is something that will actually help you out. So it was able to sniff it, and it was able to kind of figure that out. Now, granted, this is one interesting detail though. Even if you look at the merge join, my estimated number of rows is still dramatically different than my actual. So it's an improvement, but it's still a bit off. And if you look at the I/O, we'll see that behavior as well. I have to create a work table, which I don't scan 500,000 times. I scan about 93,000 times, but it still does a heck of a lot of I/O. Not nearly as bad as 1.5 million. This is about 1.18 million, but still a fair amount of I/O here. And then everything else is fairly negligible. So this is a case where it's improved things, but it hasn't magically solved the problem entirely. And interestingly enough, one of the key differences is that we don't have statistics on table variables. So all the query optimizer is doing is looking at the number of records, but it has no idea about the data distribution, which is another key factor that comes into play when you're doing when you're coming up with that execution plan. So that's one of the drawbacks here, and that's one of the reasons why it still wasn't able to come up with an optimal plan. And in fact, the optimal plan using that table variable is actually to have a hash match here. So I'm going to use a table hint just to force the hash match, just to show you that particular behavior and that particular difference. So we have the hash match join here, and then I'll just show this from the I/O numbers here. 1,000 logical reads against the that particular table there, and then just to prove the point, 800 logical reads over here. So in total, under 2,000 logical reads, because in this case, again, a hash match join is far, far more efficient. But again, the query optimizer wasn't able to figure that out because it doesn't have information about stats. If it had information about stats, it would have done a hash match join like it does with the two temp tables. I swear it's so funny trying to say table variables versus temp tables and going back and forth between those. All right. So in either case, that concludes this particular demo. I'm going to turn on batch mode for row store. And if you want to, this is an optional thing. Batch mode, once that is turned back on, because I had intentionally disabled that earlier, you'll actually get an even greater benefit from it. But you can mess around with that examples later on. We have to get back to the regular presentation. So consider that bonus material. Okay, any questions about table variable deferred compilation at this point?
I don't see any questions.
Yep, doesn't look like there's any questions. I just glanced at that as well. So, all right, let us continue. Next topic, inline scalar valued functions. So I've also disliked scalar valued functions. If you're familiar with me as a speaker, I have half of an entire presentation about why I hate UDFs. And what is a UDF? Essentially, a UDF, or a scalar user-defined function, is a function that exists within a select statement, right? So you see the select column 1, column 2, DRY. So what does DRY stand for? Well, if you're a developer or have a computer science background like I do, many of us are taught with procedural programming languages. And those languages have a concept in there called DRY. Do not repeat yourself, or don't repeat yourself, I should say. And the thing is, the idea there is that you want to write your code once. I don't want to write the same set of code in multiple different places and copy and paste it. So you have things like functions, you have things like classes and object-oriented programming and such. That's that way you can reuse chunks of code. So you only have to maintain it in one place, but it can be called from multiple places. The problem is that T-SQL is a completely different kind of language than most other programming languages. It's something called the declarative language. And unfortunately, procedural paradigms or algorithms such as functions and things like that perform horrifically in declarative languages. And particularly, you get a behavior called rebar in this particular example, row by agonizing row. So what happens here is that the contents of that function, that code of that function, gets executed once individually per record that comes back from the outer select statement. So if that select statement returned 5 rows, the code inside that scalar user-defined function would be executed 5 times. But if it returned 5 million rows, that code inside will be executed individually 5 million times. So that's not good times. That's a lot of extra overhead. And remember that T-SQL excels at doing things in a set-based fashion, not an iterative fashion. So what is inlining? So the idea of inlining is that it's going to transform the rebar code for you, in that the rebar code is essentially executed in its own little session, if you will, but instead now it's going to try and merge everything back into that one single individual T-SQL statement. So that's the idea of rebar, or of inlining that rebar code away. Now, unfortunately, as of right now, this is a V1, so it has a horrifically long list of limitations, although this can be found in the Microsoft documentation website. I don't mean for you to read this right here, just to understand that, yeah, there's a lot of gotchas to this. But nonetheless, turning this on could be very powerful, and it could help some of your existing workload out. So with that, I want to show you this particular demo. Okay, I think you'll like this little subline here, the SQL Server 2019 that broke some of my old demos here. So we're going to turn off scalar UDF inlining, and I'm also going to do a little bit of setup here of just creating a couple of indexes. So while that setup code is running, basically I have a simple select statement, select top 20,000 here, and then calculate net profit, calculate sales commission, interjoining inventory and sales history. So that's our example statement here. Let's take a look at the volume of logical reads here. So according to setstatistics.io, we only did 286 logical reads. That's not much, right? Look at our elapsed time, close to 5 seconds. So here's the thing. Remember how I said scalar user-defined functions are essentially executed in their own session, if you will. I use air quotes around that, but essentially it's executed as a separate statement. And you see that behavior in many different ways. One of the different ways is the fact that we actually have 3 different execution plans here. One is for the overall query, but inside the compute scalar are 2 expressions, and those 2 expressions happen to be my scalar user-defined functions, which have their own execution plans here. One is an index seek against two tables, the inventory and sales history table, and another set of queries here for sales commission that goes against inventory, sales history, and salesperson once again. So you'd see that I'm redundantly going back to the same tables over and over and over again in the context of these scalar user-defined functions. Why do that extra overhead? Well, what do you mean, Andy? What overhead? What extra I/O? We didn't see it inside set statistics I/O. Unfortunately, scalar user-defined functions, their I/O overhead is hidden from set statistics I/O. Now, in SQL Server 2016 or higher, they introduced sysdmexec function stats, which now gives you information about, well, all the functions that have been running in your environment. And I dare you to run this in your environment if you know you use a lot of scalar user-defined functions, because you might be horrified to find out some of the underlying information. So in this case, here's my two scalar user-defined functions executed just over 20,000 times. And here's the actual logical reads, 120,000 logical reads, 164,000 logical reads, only for 20,000 records. So that's a heck of a lot of extra overhead. And that definitely wasn't the 200 or 300 some odd logical reads that we thought we saw in set statistics I/O. So a lot of extra work went on behind the scenes. So what inlining is all about is that it's going to combine those three estimated execution plans or three execution plans all into one single execution plan. Remember how we had, three different plans before? So I'm going to turn on scalar user-defined or scalar UDF inlining. First, I'm going to show you that it's turned off just to prove it. Value is 0. Is this the default value? It's not the default value. Let's turn it on here with this database scoped configuration command. And now let's run our example query once again. Hey, this executed a heck of a lot faster. Remember the prior original version executed in 5 seconds? This executed in less than a second. And now I see my I/O counts. Now I'm still doing a lot of scans and such like that, but you know what? This is still more accurate at least, and now I'm actually seeing the true resource utilization because the query optimizer is now again combining those three different SQL statements all into one. So it's not a magically huge improvement, but it is somewhat of an improvement. So it's a better than nothing. And remember, that's kind of the idea of some of these features. Hopefully, just by flipping the switch and turning these on, they can at least hopefully improve some of your T-SQL code. Even if it doesn't improve everything, maybe if it improves 60 or even 40% of it, that can still potentially be a huge win. And that's the idea of all of these different features. Hopefully, again, that they will help you out and be that pseudo easy button for you. So let me just give you a estimated execution plan, and now you see that there's just one gigantic execution plan here that is a bit better rather than those three hidden ones, and we're not doing things in a row by agonizing row fashion anymore. So you can make use of SysSQL modules to figure out whether something is inlineable or not. So there's some additional information here. So you can use this, right now to try and figure out what code base in your existing databases are inlineable once you've, of course, upgraded to 2019. More information here at this URL. Now, for what it's worth, I still dislike scalar user-defined functions even when they're inlined. And to drive that point home, I'm just going to write a flattened query that has ripped out all that DRY code and flatten everything here. And then we're going to compare and contrast that to the inline UDF. So both of them executed very, very rapidly, but the one with the scalar user-defined functions, 625 milliseconds, compare that against 53 milliseconds. That's still a heck of an improvement. And instead of the ridiculous, I/O and the, hundreds of thousands of logical reads, because I flattened it, SQL Server is able to do an even better job on figuring out exactly what I need. And in this case, it only does a few hundred logical reads. So this is a huge improvement compared to, the use of the user-defined functions. The inlining of them definitely helps. So if you can't modify your code, then hey, definitely do that. It's a better than nothing, but ideally you still want to modify your code. So that's a lesson of this. All right. So, any questions up until this point, by the way? Let's check out the questions pane. Will all these sessions be recorded for later viewing? Yes. Oh, you answered that already. Are there any drawbacks to turning on inline UDFs? Well, they may not work for everything. There may be regressions. There's always a risk of regression, so test, 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 of course. And then yeah. So basically, you just kind of want to just test, test, test. And is inlining available only in SQL Server 2019? Yes, that is correct. Inlining is only available in 2019. That's what this is all about, intelligent query processing from 2019. Okay. Doesn't look like there's any other questions, so let's continue onward. Batch mode for row store. So first of all, what is batch mode? Well, we all understand that T-SQL does work in a set-based fashion, right? Well, here's the thing. What if I told you that technically that's not quite true? If you actually break out the debugger and you look behind the scenes at what SQL Server is actually doing when it's retrieving data and such, traditionally with row store constructs, it would actually still be grabbing records row by agonizing row. It's kind of an interesting little tidbit of detail. But for all intents and purposes, for what matters to us, we don't need to be worrying about what really happens behind the scenes. We still need to think of and approach T-SQL in a set-based fashion. But in either case, what's really cool is that, a while ago when SQL Server introduced column store, they were able to introduce something called batch mode, such that instead of grabbing things row by agonizing row, they were able to grab, batches of records and do operations against that. So they were able to implement true set-based operations behind the scenes when it gets into the nitty-gritty. So yeah, like I said, it used to be only available for column store, but now in SQL Server 2019, batch mode is finally available for traditional row store constructs. And that's where this shines, because once you have batch mode, a whole bunch of other things are now available to us, as we talked a little bit about before. Or actually, that's coming up next. So one of the things that's now available to us as long as you're using batch mode is something called adaptive joins. So remember we talked a little bit about nested loop joins and hash joins. I mentioned that nested loop joins are ideal if you have one data set that's very small and another data set that's very large, versus a hash join where you have a large data set versus a large data set. Well, what if you have bad estimates because you're still using table variables? So a nested loop join gets chosen when you really should be using a hash join. Remember those examples from earlier in the demo? That would be an example where adaptive joins would be very useful, because what happens is that SQL Server will begin execution and using one or the other that it believes is ideal, but if it sees it's terrible, it'll switch to the other. And that's the point of the adaptive join here. It can essentially change its mind at runtime, is essentially what it comes down to. And it can be very, very cool. Again, this is only available for queries that leverage batch mode. And there's, of course, caveats to whether a query can even go into batch mode versus row mode. But still, it can potentially benefit a good number of your existing workload. The other capability that's now available to us now that we can do batch mode and row store is something called memory grant feedback. So whenever a T-SQL query and an execution plan, or you come up with an execution plan, you basically also tell the storage engine that, I need a certain amount of memory in order to do work, because I'm sorting data, because I'm doing hash joins, or whatever the case may be. It's like you saying, if I'm going to work on this problem, I need a certain amount of extra space to work on it. Like pretend I'm in the kitchen. I need this amount of workspace to make dinner for you tonight, right? So that's me kind of coming up with that idea or that estimate of what is it that I'm going to need in order to do this work. And that's what the memory grant is. So once again, do we always make the right guesses? We already see that based upon estimates, we may not make the right guess. So the idea of memory grant feedback is that, okay, I've executed this query once. Yeah, my memory grant was either way too large or way too small. So the next time I execute this piece of code, I'm going to make an adjustment. I'm going to try and find that sweet middle spot based upon what happened last time. So it won't help that first execution or that immediate execution, but at least we can help us for subsequent executions. And this is really great if you have code like stored procedures that are run on a repeated basis in your workload. So memory grant feedback can be very, very powerful. So with all of that, let's dive back into the demo and explore all of these. I did not have that file open. Memory grant batch mode. Okay, so first let's just introduce batch mode. I'm going to turn that on right now and make sure it's on. Also have set statistics, time, and IO on. Just to prove to you that it's on, I'm going to show you the database scope configurations. And I apologize, I meant to turn it off, not on. So we're going to show you kind of a before then after, like we have in elsewhere. Okay, so first we're going to do a small data set, and I'm just going to do some aggregations here. Basically, got a sales summary table, between these two particular dates, and then an almost identical query without the constraints. So basically, an aggregate query with a small amount of data, aggregate query with a large amount of data. Got to turn on actual execution plan, and let's take a spin and run these guys. So first of all, let's look at logical reads, about 3181 for the small data set, 3354 for the larger data set. So it's actually really not that much of a difference. Execution times, 143 milliseconds, 74 milliseconds for the smaller and the larger. And then here we see that we have a select, and where I'm doing a clustered index scan, hash match aggregate here, and so on and so forth. So really what I want to show you is the properties tab. So I'm going to pop that open and I'll pin that out now. So when I look at one of my different operators in the execution plan, it'll show me the actual execution mode, row mode in this case. So I was looking at that sort operator. I should have actually gone over to the table operator here. So in this case, on the table operator, the clustered index scan, actual execution mode is row mode here. Okay, so that's where you see what's actually going on. And this is where we also estimate what did we want to try and do, because there are situations where we want to do batch mode, but we cannot because of one of the various limitations, all in the documentation. All right, so let's turn on batch mode. Now let's compare and contrast the results and how these two queries operate. So from a messages perspective, that smaller data set really didn't improve. In fact, it's almost identical. On the other hand, the other one did speed up a little bit. So that's pretty cool. IO is fundamentally the same. Let's look at the execution plans. So for that smaller data set query, actual execution mode is still row mode. That's why we didn't really see any functional change here. On the other hand, that larger data set was able to benefit from batch mode here. So we see that in that other data set, that larger data set, we did go into batch mode here. So that's one of the reasons why this was able to go a bit faster and run slightly more efficiently. So here's the actual number of batches that it processed, 556 of the 500,000 records here. So you can get at some of the more interesting discrete details, which is actually pretty cool if you really want to get into the nitty-gritty details here. And notice, by the way, storage. This little detail point here is showing me that this table is a row store table, not a column store table. I'm not playing any tricks on you. There's no column store behind the scenes. So, again, this is where, again, you can prove out that this is the type of index or table that we are going after, not column store. So one key takeaway about batch mode in of itself is that batch mode will only help reduce CPU consumption. It actually doesn't really help IO from a pure IO perspective, because you still have to read those data pages regardless. So if your bottleneck is IO related and data is not already in the cold cache, then batch mode again will not really improve query lapse time. That's one of the reasons why in my prior example I intentionally did some aggregations to show you that it's performance improves, because, well, aggregations are CPU intensive. So I specifically chose that example here. So again, more information about that here in the source. So a little bit of trivia, 131,072 records is apparently the magic cutoff point as far as whether you're going to go from row mode to batch mode. So I'm just going to use tempdb here, and I'm just going to do a little bit of setup. I'm going to create two temp tables, one with 131,071 and another with 131,072 records inside here. So this is just my quick bit of setup. Again, this is more just trivia than anything else. Setup is done. So I'm just going to run a quick sample query against both tables to show you the execution plans. Let's see, here's the table. Here's the first one where we are underneath the threshold. Execution mode is row because we're underneath that threshold. Second one has a simpler execution plan, interestingly enough. And we have batch mode here. So, and for what it's worth from an execution time perspective, 397 milliseconds on the CPU, 42 milliseconds on the CPU. And remember, these were some queries. So again, they're CPU intensive queries, relatively speaking. So even though my actual elapsed time was a little bit higher, it actually helped out a heck of a lot in this simplistic example on the CPU. So if you're CPU bound, this is a great place where it could potentially help you out. All right. Now, again, batch mode in of itself is not the huge benefit as far as intelligent query processing is concerned. It's the fact that we can do batch mode on row store that enables us or unlocks the power for us to do memory grant feedback and adaptive joins. That's where the huge power comes in. So let's go to our adaptive join, or no, this is the memory grant demo now. Once again, SQL Server broke one of my old demos, which is kind of funny. All right, so let's just do a bit of setup. And I'm going to turn off adaptive joins. I'm also turning off memory grant feedback. Notice that memory grant feedback has two database scope configuration values, one for batch mode and another for row mode. So, that's the other cool thing about memory grant feedback is that it's available in both. Forgot to mention that. So we see it's turned off for both. So here's our test query. It's another aggregate query here against inventory, sales history, and customer, blah, 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 blah. So let's take a look at what the memory grant is. I need to have this pinned out once again. So if I go into the execution plan, so if you want to get into the nitty-gritty of the memory grant info, you can look at all of these underlying details. But frankly, all we really care about is the memory grant up here. So this is in kilobytes, so it's almost 900,000 kilobytes. So I'm just going to write that here for future reference so we don't forget it. So let's turn on both memory grant feedback for both row mode and batch mode. And then I'm going to rerun my test query. Oh, whoops, I need to open that out now. Okay, so now inside memory grant info, we still have the same exact memory grant. Is memory grant feedback adjusted, yes or no? In this case, no, because it's the very first time we've executed this piece of code after we turned on memory grant feedback. Notice that we also have a different value, says last requested memory. So this is what we had the last execution. So you will see the next time we execute this, that there will be a value here. But again, this is the first time we ran it and we didn't have a really good memory grant here. So let me jump back over here and rerun this guy. Execution plan. Whoops, I need to expand this out. Look, instead of nearly 900,000, 900,000 kilobytes, we're down to 300 some odd kilobytes, 300,000 that is. Is memory grant feedback adjusting? Yes, we are in the process of adjusting. We can still fluctuate, in subsequent executions, but this is still a heck of a lot better than that 900,000. We've reduced the amount of memory that we need in order to execute this query. So that's really cool. So let me do this one more time. And now finally, we have a memory grant feedback adjusted, yes, stable. We've stabilized here. There hasn't been a lot of dramatic changes. So you know what, we're just gonna stay here. So we're calling this good. So that's a much, much more reasonable memory grant. But here's the thing, that was just a very static example. But the thing is, we run code with parameters. We run code that has variable volumes of data that gets returned on a regular basis. So to help test that, I'm going to be using this store procedure get sales summary by year that takes a start date and an end date. And it's our same query from before, except I have this where predicate that has, again, different date ranges that'll be passed into it. So what I'm going to do here in this example to show you something interesting behavior about memory grant feedback is that I'm going to free the proc cache, and then I'm going to run my store procedure 3 times, and I'm going to run it with 3 different date ranges. First execution has about 1 year of data. This will have from 2017 to 2020, and then this one is going to have many, many more years of data. So I'm going to get bigger as we go, and let's see how the memory grants change. So jump over to the execution plan. First guy here, memory grant info. About 500,000, 500,000 kilobytes. No first execution, of course. I'm going to jump down to the third one because we'll see what the second one had adjusted to in the last column here. So in the second execution, it readjusted to 136,000, but it found that, you know what, I still need to keep readjusting here. And part of the reason is that as I'm executing with different values, we're actually getting, we need different amounts of memory. So we're going to constantly keep adjusting here. So if you have very parameter sensitive code where the result sets could vary wildly, you might be constantly readjusting your memory grant feedback. You may not be able to get to a stable point in time. So that's one interesting caveat about this memory grant feedback here. So let me also go from large to small, because notice I also went from small to large here, right? Just to illustrate a point. So I'm going to go from large to small. The initial one, just to show you that briefly. Once again, about 900,000 kilobytes. And then let's go to the final one. 300,000. I forgot to show you the interim. Oh, but in this case, from large to small, we actually stabilized. So because the thing is, the large gave us that bigger ballpark, that medium one gave us a more reasonable size of 300,000, and then that small one fit within the medium one. So you know what? We think we stabilized here. But remember, with the small to large, as I kept getting larger, I kept figuring out, oh, I need more memory, I need more memory. And that's why we're still adjusting. So what do you think will happen depending on the first query that's into the plan cache? Because caching is one of the kind of caveats here. And where do we actually get started? So are you going to go from small to large, large to small, and so on and so forth? So if your first query in happens to be a fairly large data set, then most of the subsequent ones will be smaller, you'll probably be all right. But again, where are you going to fall depending on the nature of your query execution is kind of one of the consequences of this behavior. So here's a quick little cheat sheet of the different memory grant feedback adjusted values. I'm not going to go through these. You can read this all on your later here. But note that for parameter sensitive plans, memory grant feedback will eventually disable itself. So don't worry, this is not going to go completely hog wild. If you have a lot of code that is parameter sensitive and is all over the place, SQL Server will eventually give up and say, you know what, this code is way too crazy. I'm not going to bother trying anymore, which is actually a good thing. So it'll just go back to its traditional behavior. All right. So with that, let's go on to our final demo on adaptive joins, and it looks like we're fairly good on time. So excellent. Do a little bit of setup here. I'm going to create a couple of non-clustered indexes. All right, so the query that we're going to be using here is getting the number of vehicles sold by state. Okay, so we pass in a state value and then we do some aggregations and so on and so forth here. So just to show you what the distribution of values are from the customer table to the states is that the vast majority are in Illinois. Massachusetts and Wisconsin have a fair number at around 100,000 or so. And then most other states are at either 20,000 or less. So again, that's what the distribution is. Remember, Illinois, Massachusetts, Wisconsin, and then pretty much everyone else. Because again, sizing and data volume will come into play. So I'm going to turn off adaptive joins first. Show you that it's off. Yep, no tricks up my sleeve. So first of all, we're going to go with a medium data set. I'm going to use Utah here, and I'm going to free the proc cache, and I'm going to execute this guy, and this will be kind of our baseline here. So from the messages tab, we have about 13,000 and 9,000. So I'm going to ballpark this at what, about 24,000 logical reads. Close enough. So we'll just write that down. And then inside the execution plan here, we have two different hash match operators, going against, customer and sales history and inventory, okay? So what happens if we have a small data set, like Alaska? Messages tab, heck of a lot less I/O. This is what, 485, about 7,000. I will mark that down. And then in the execution plan here, we have nested loop joins. Whoops. We have nested loop joins here because remember, small data set, large data set, right? So nested loop joins excel in this particular example. Now, if I rerun the large data set example here, remember I did not run free proc cache, so we're going to use a cache execution plan here. And this is where parameter sniffing, becomes an issue, if you will, depending on how how varied your data set happened to be. So in this case, we ran with a larger data set, but we also did the nested loop joins once again, which did not serve us well. So in this case, our I/O is ridiculous. 700,000, 300,000, well over 1 million logical reads because we did not get an ideal execution plan, because we did not get ideal joins, right? So that's where this is sad times. So let's turn on batch mode and adaptive joins and see how that can help us. So I'm going to free the proc cache and I'm going to run this once again with a medium data set just to show you the behavior. Inside the execution plan now, let's open this up. I'm going to turn on the Properties tab as well to show you some details. Okay, so first of all, you see a brand new operator here called adaptive join. And instead, there's actually 2 references to the inventory table here, joining against sales history. So that's kind of one interesting behavior. And then when you start mousing over and going after the underlying details of each of these, adaptive join, I get a different description here, choosing dynamically between a hash join and a nested loop join. What I believe I'm going to need, here's the estimate, will be a hash match, and here are my underlying estimates. But my actuals wound up being a heck of a lot less. So we wound up just going with a nested loop. Nested loop in this case is okay. Here's the threshold of what we needed to fall under in order to switch. That's what we came up with in the execution plan when we were basing this off of our estimates. And that's a key statement there. I was choosing my words very carefully here. So in this case, the actual, again, falls underneath here. So you know what? We're just going to stick with the nested loop join. Otherwise, if the actual had been higher or we started exceeding that 60,000, then we would have flipped over at that point. Okay. So let's free the proc cache and let's take a look at what it looks like with a small data set here. And with a small data set, we didn't actually exceed any kind of threshold because we never got into batch mode. So we have a traditional execution plan here with the nested loop join here. And you can see, for example, that we are in, I'll just do it on the tables themselves, I should say. Yeah, customer sales history. Basically, if you click on any of the different tables, you'll see all of the actual execution modes are all row mode. Because again, we're working with too small of a volume of data. We're not going to exceed that threshold to get into batch mode. So batch mode is not available to us. Therefore, adaptive joins are not available to us. So once again, the planned cache and who gets into the cache first matters here. So let's free the proc cache, and I'm going to run a large data set first and then a small data set thereafter with the cached execution plan. So of course, we know that the first, with the large data set, we're going to get an adaptive join into the execution plan. And in this case, this guy here, well, we actually saw the behavior earlier where it wound up switching and doing a hash match in this particular example. And then with the second smaller data set, we're able to leverage the execution plan that was cached, and we're able to leverage the adaptive join. Even though it's a smaller data set, remember the exec plan is what determined what we're going to do, so we're still able to leverage the adaptive join here. So that's good. However, if we free the proc cache and the first one in happens to be a small data set, the other data set will not benefit, or the other execution will not benefit from an adaptive join. In fact, they will both suffer from nested loops here. So that's one drawback here, is because of the plan cache and plan caching type issues. So that's something to be aware of, especially if you want to leverage adaptive joins in batch mode here. So this is a different type of example. I'm not going to go through it right here, but I'm basically bouncing between large and small data sets, and you can experiment with that. Okay. So with that, I want to wrap up and leave you with some parting thoughts. So as you can see, and hopefully you have a good sense that there's a lot of really cool features in intelligent query processing, and there's a lot of really cool ways that this code or this functionality can help your existing code base. but there are pitfalls as well. So I encourage you to be cautious, especially with parameter sniffing and caching issues. One thing we did not have time for is that there was actually an optional demo for table variables where parameter sniffing issues can also really, really burn you there as well. That's included in all my demos, but I chose to skip over that one just because of time. But go back and play with that one as well. So table variable deferred compilation is also suspect to parameter sniffing type issues. Nonetheless, I still encourage you to not be afraid and to give this a try. We all have test environments. Test out your workload, test out your legacy code base here. Because frankly, it's a situation of if this can help benefit even 50% of your code base and improve performance across the board without making a single code change, then why not? Why don't we want to improve performance in our existing legacy applications, right? And remember, you can use database scoped configurations to make changes. Like say, for example, in a given database and its workload, table variable deferred compilation is horrible for you. But you know what? You can still benefit from adaptive joins and or memory grant feedback. So you can turn those on and off willy-nilly. That's the other cool thing about this. And in general, stop thinking about the version of SQL Server that you're on. Start thinking in terms of database scope configurations. Microsoft has given us a myriad of different ways of controlling different functionality. So if you still need legacy functionality, still upgrade to a newer version of SQL Server. You can use things like database scope configurations to turn off those new features in order to, again, make use of like database compatibility mode as well, to make use of or simulate, if you will, that older version of SQL Server. Don't be afraid of new versions, because again, you can operate under the same working conditions, if you will, of the older versions. Microsoft has made huge improvements in that capability to turn those knobs and turn those switches, if you will, without resorting to the traditional trace flag. Okay, with that, I just want to say thank you so much for joining me. It looks like we came in just at time. I'll stick around for a few minutes for questions. But remember that GitHub up here. So that GitHub will have a copy of all my slides and my scripts and also my demo databases if you want to. Again, my contact information is down there. So with that, thank you again, and let's see what we have in the questions tab.
Yeah, we have one question.
Okay. Can adaptive joins benefit from option recompile in store procedures? Yes, absolutely they can, because so if you use option recompile, at that point now you are recompiling that execution. So it'll help you avoid that scenario of a plan getting cached that does not have an adaptive join in it. Now, of course, the trade-off is that now you're constantly recompiling it, and in some regards, the adaptive join in of itself is almost not that useful to you, because the idea of the adaptive join is for that execution plan to be able to make a decision on the fly. If you're going to use option recompile, you're coming with a brand new execution plan every single time. So yeah, it can benefit from it, but again, everything is a bit of a trade-off. Are you better off preceding your plan cache, or again, just not using adaptive joins whatsoever? Again, a little bit of a trade-off here, but at the root of it, yes, it technically can. Great question. Any other questions?
So you have one more from Jesse. Can adoption joins benefit from option recompiling store procedures?
That's actually the question I just answered.
Yeah. No.
Awesome presentation. The scripts are, again, located in one of the repositories in that GitHub URL that you happen to see up on the screen. So again, reference that GitHub. All my repos are up there. Everything should be public. All right, so if there are no additional questions, I do want to remind you that I'm going to be now jumping over to the SentryOne office hours. I hope you take a few minutes not only to visit me at SentryOne, but please visit all of the sponsors, because the organizers of this event can't put this event on without sponsors, and frankly, we need ROI, and this is all uncharted territory for all of us. So please visit all of the sponsors today. Give us all some love so that we can all continue supporting these virtual events and continue forward, so that we can continue sharing all sorts of awesome, free information for you as well, as we adapt to a new world, right? So please visit all of the sponsors today. Hopefully visit me too, but please visit everyone. And with that, I think I will wrap things up. Thank you once again for joining me.
Thank you. The virtual applause.
Yes, yes, yes. All right, so it looks like everyone has a few minutes for a break. And so, yeah, all right, I'm going to drop out and I'm going to jump on over. So thank you once again. And
Okay, see you
Cecilia,
in
I'll
1
talk to you
hour.
in about an hour or so because I'll be
Yes.
back here for my vendor presentation.